In this lesson, we're going to continue to think about colligative properties. Specifically, we're going to focus in on freezing point depression. Recall that a colligative property is a property that depends on solute concentration only, so how much solute is there. Now, here's the thing, a new little wrinkle to our colligative properties that we're going to add for this lesson. Dissociation does matter. So, for example, if I put sodium chloride into a solution, it splits apart into sodium plus and chlorine minus. That doubles the effective concentration of different particles in my solution. So it's not that it's sodium chloride that really matters, it's the number of particles dissolved. But sodium chloride, because it falls apart into two, has a larger impact than a single molecule of, say, sugar, which doesn't dissociate. When I put it into solution, it stays all together. Okay? So when we take a look at this truck down here, it's spreading salt. And one of the reasons it spreads salt is because the sodium and chlorine dissociate and break apart into sodium and chlorine, and that's going to give it a greater freezing point depression. So in this lesson, we're going to focus in on freezing point depression and also think about how the dissociation changes these colligative properties. But what we say here about dissociation applies to all of our colligative properties, as we saw in osmotic pressure and also for vapor pressure lowering and boiling point elevation. Okay, what is freezing point depression? As we've already suggested, freezing point depression is a decrease in freezing point by adding a non-volatile solute. So when my truck spreads salt on the roads, it dissolves in water, it dissociates in the water, and then it lowers the freezing point. That means it has to get even colder before the water on the roads will freeze, and it makes it more likely that instead of having ice, we'll have liquid water, which is of course safer to drive on. Here's the mathematical expression for calculating that change. The decrease in the freezing point is equal to the freezing point dissociation constant times molality. Now, it's almost better to think about this as having absolute value bars on it, because it's a decrease. So if it's a -3 drop in freezing point, I'm going to plug in just the magnitude, just 3 there, as we'll see in a few practice problems, okay? And then the freezing point depression constant is a constant that depends on the solvent identity. So while solute identity doesn't matter, the solvent identity certainly does. The size of your change in freezing point depends on if it's water or ethanol. Your solvent definitely matters. And then lastly, we have the molality of our solute. And molality, remember, is moles of solute over kilograms of solvent. Okay, let's do a practice problem that focuses in on dissociation. First, let's just think about what dissociation does to concentration. Here, the dissociation of ionic compound increases the number of separate species in solution. Determine the effective molality of the compounds dissolved in water. Okay, so now we're going to think about how the molality of these solutions changes when I think about the fact that they're falling apart into separate things. Okay, so the first thing I'm going to do, just like I did in the osmosis video, is determine the Van Hoff factor. Remember, that's just how many ions our things fall apart into. So for sodium chloride, it falls apart into sodium and chlorine. So it's an I of 2. We already looked at that on the previous slide. Similarly, we already looked at how sugar doesn't fall apart, so it's an I of 1. Calcium fluoride falls apart into 1 calcium and 2 fluorines. So that means its I is 3. So it has a Van Hoff factor of 3. Lastly, iron nitrate falls apart into 1 iron and 3 nitrates. So nitrates is a polyatomic ion, so this thing stays together, but there's 3 of them. Okay? And so what that means is there's a total of 4 ions, 1 iron, 3 nitrates, and that means our I is 4. So now what I can do is I can calculate the new concentration by simply multiplying the concentration given by how many things it falls apart into. So here I'm going to do 1.2 times 2, and I'm going to get 2.4 for my new molality. Okay, and now for calcium fluoride, I'm going to do 0.8 times 3, and I'm going to get 2.4. So there's a tie between those two. And then I'm going to look at sugar, and I'm going to multiply my 2.0 molality times 1. And that will give me 2.0 molality. Why did I switch to blue? No reason, just for fun. Okay, then 0.8 times 4. That's going to give me 3.2 for my molality. Okay, now the reason that's relevant is because remember, the number of individual little non-volatile solute particles in solution is what determines the freezing point depression. So now we could ask another question, which is what substance below would lead to the lowest freezing point of water? So I go and I dissolve all these in water. What's going to lead to the lowest freezing point? Well, for all of them, their KFs are going to tie. The KF is the same because it depends on water, and they're all water. So all that matters is the molality. The bigger the molality, the bigger the change in freezing point. So all I have to do is identify the biggest molality. That's going to give me the biggest freezing point depression. And that would be for my iron nitrate. So iron nitrate, because it has the highest effective molality when I take into account dissociation, is going to lead to the greatest freezing point depression, and therefore the lowest freezing point for water. Okay, so here we've just thought about how dissociation plays a role there, but our colligative properties allow us to do one other cool thing. And we'll do a practice problem of that right here. They actually allow us to determine the molar mass. How is that? Well, let's look at this problem and we'll talk about it as we go through it. 200 grams of an unknown covalent compound is dissolved in 2.2 grams of water with the Kf of 1.86 degrees Celsius per molality, and a freezing point, a normal freezing point, of 0 degrees Celsius. If the new freezing point of the compound is minus 3.2 degrees Celsius, what's the molar mass of the compound? Let's think about why this works, right? Because the freezing point depression depends solely on how many separate particles I have, which doesn't depend on mass, but on molar mass, right? If my molar mass is 200, then I have 1 mole dissolved. If my molar mass was 50, then I've actually dissolved 4 moles here. Okay, so I can actually backtrack from a freezing point depression to the molar mass of my solute. Let's go through that step by step. The very first step is to determine the molality. Okay, and I'm going to do that by using this expression and just going backwards. So that's step 1. And here I already know that my change in temperature is 3.2 degrees Celsius. And remember, we said we should really use absolute value for this. So it is a drop of 3.2 degrees Celsius, which gives you minus 3.2. And the magnitude of that change is 3.2 degrees Celsius. So that's what we're going to write down. And then we know the Kf, which is 1.86. So what that means then is we have all the variables. Let's go ahead and add those units, degrees Celsius per molality. We have all the variables except molality. So let's do a little algebra. We have delta Tf equals Kf times molality. If I want to rearrange and solve for molality, all I need to do is divide both sides by Kf. Okay, and once I do that, my new expression is change in temperature divided by my Kf is equal to my molality. So if I plug in my change of temperature of 3.2 degrees Celsius and I divide that by my 1.86, I will get the molality. It turns out to be 1.72 mole. So that's the molality. Okay, the molality critically is connected to the moles, which is connected to the molar mass. So let's go through step 2, which is determine the moles of solute. Okay, so the moles of solute we're going to get from the molality. So here's my molality expression, and this is the equation we'll use in step 2. Molality equals moles of solute divided by kilograms of solvent. And notice we've been given kilograms of solvent, how many kilograms of water there are. Okay, so what I'm going to do then is once again do a little algebra where I know molality is equal to moles over kilograms. And to get kilograms over on the other side, I'm going to multiply both sides by kilograms. And that's going to give me the expression kilograms times molality equals how many moles I have. All right, so in this case, that means that I'm going to take kilograms, which is 2.2, and I'm going to multiply it by the molality, which we just calculated in the last problem is 1.72. And when I multiply those together, I'm going to get 3.7849 moles. There's actually more digits, and I'm going to keep all those in my calculator that I'm going to use for the next step. So notice, I know I have 3.7849 moles, and I know I have 200 grams. So because I have mass and I have moles, that allows me to find molar mass, and that's step 3. Step 3 is going to be finding molar mass. Remember that the definition of molar mass is grams per mole. So this is the equation I'm going to use here to go ahead and calculate the molar mass. No algebra needed here because I already have molar mass, which I'll abbreviate MM, is equal to grams over moles. And I have both grams and moles. So I'm going to plug in grams up top, which is 200, and I'm going to plug in moles on the bottom, which is 3.7849. Now notice my grams actually only has 1 sig fig, so I'm going to have to round here to 1 sig fig, and rounding to 1 sig fig, I'm going to get 50 grams per mole as my molar mass. So because I know the freezing point depression, and because that depends only on the number of particles there, then I can go ahead and calculate that by using this freezing point depression. One last note here is we assumed that it didn't dissociate or split apart. And we could assume that because it's a covalent compound, right? So we never we never had to take a look at how many parts it's dissociated into, and it's because it's a covalent compound which didn't dissociate. So that's how you can use colligative properties to actually go backwards to molar mass. And you can use that with all of our colligative properties, not just freezing point depression.